morning, student. Today we will discuss measurement of electrode potential in lecture number 2, chapter number 3, electrochemistry. In the last lecture we discussed electrochemical cell by taking the example of linear cell. We also know the electrode potential, definition of a cell potential, EMF. This work based on the redox reaction. Now a question is how to measure the electrode potential. Chemical cell, electrochemical cell work based on the redox reaction. That means simultaneously oxidation and reduction reaction take place. Now in an individual half cell there is no possibility of the redox reaction. That means half cell act as an anode, otherwise half cell act as a cathode. That means we have to measure the electrode potential of the half cell with respect to another half cell. That means we can measure the electrode potential of a cell. That means for measuring the half cell potential, we have to make the complete cell. That means with reference to other half cell, we can measure the electrode potential. For that, standard hydrogen electrode SHE is taken as a reference electrode. That means we can measure the electrode potential of this half cell with respect to standard hydrogen electrode. Now what is the construction of this half cell? So construction is similar to other half cell. Here electrolyte solution is H plus. Concentration is 1 molar because it is in a standard condition. Now temperature is 298 Kelvin. Here hydrogen gas is involved in reaction. The pressure is 1 bar because in standard condition. Now this is the platinum, rolled platinum, in which this is the finely divided platinum coated on platinum foil. Now we are passing the hydrogen gas. When we are passing the hydrogen gas, then this half cell as an anode or cathode. That means oxidation or reduction reaction take place on the platinum surface, on this platinum electrode. We know very well platinum electrode act as an inert electrode. Two types of electrode are there, reactive electrode and inert electrode. Metal electrode like copper, zinc, they are reactive electrode. That means they participate in a chemical reaction. Here platinum, graphite electrode, gold electrode, which are inert electrode. Inert electrode, that means they do not participate in chemical reaction. They just provide only surface for the chemical reaction to occur. Here also platinum provides the surface. Now this half cell act as a anode or cathode. Suppose this half cell act as a anode. This half cell act as a anode. Then oxidation reaction take place. Oxidation reaction take place. That means we are passing hydrogen gas. This hydrogen gas pressure is 1 bar. That is converted to H plus into electron. Here concentration is 1 molar. We have to maintain. This reaction is take place. Suppose this half cell act as a cathode. That means reduction reaction take place. That means H plus concentration is 1 molar is reduced to 1 by 2 H2, gas pressure is 1 bar. We have to here maintain the pressure 1 bar and concentration also 1 bar. That means this half shell having tendency to release the electron, otherwise receive the electron. Both tendency. Each half shell having both tendency to release the electron and to receive the electron. And this tendency is we know that is called the potential, electrode potential. That means when electrode is contact with electrolyte, the potential difference is developed. That is electrode potential, which is reduction potential. Suppose reaction take place, or oxidation potential. Suppose oxidation reaction take place, standard condition, then it is known as standard oxidation potential, standard reduction potential. Remember, for each electrode, standard reduction potential and standard oxidation potential are equal, but the only sign is positive and negative. That means reduction potential is positive, then oxidation potential negative. Oxidation is negative, then reduction is positive. Now, by conventional system, otherwise IUPAC has accepted for this standard hydrogen electrode, this standard reduction potential and standard oxidation potential is taken as 0. That means standard reduction potential, standard oxidation potential of this cell is accepted as 0.0 volt. Now when it is accepted as 0.01, then it is easy to measure the standard electrode potential of other half cell. Now this is the construction of standard hydrogen electrode and their information. Now topic is the measurement of electrode potential. Now how to measure the electrode potential? We have to measure the electrode potential of other half cell. The simple method is that the half cell whose electrode potential to be measured, that is connected with this standard hydrogen electrode. We have to connect this with standard hydrogen electrode. Make the complete standard cell and measure the potential by using the potentiometer. Potentiometer gives the exact value of potential. Voltmeter gives the approximate value. That means, suppose we have to measure the electrode potential of a half cell. This is a half cell whose potential to be measured. Now this is connected with a standard hydrogen electrode and we measure the standard cell potential. Standard cell potential is measured using the potentiometer. So we know standard cell potential formula is E reduction cathode minus E reduction anode. That means standard cell potential is the difference of standard reduction potential of cathode minus standard reduction potential of anode. Now, standard cell potential is measured using potentiometer. Suppose this value, standard cell potential is a value, suppose we are taking 0.6. Otherwise, directly there is two possibility. We are taking the two possibility. Suppose a standard hydrogen electrode act as an anode, then other half cell act as a cathode. Standard hydrogen electrode act as a cathode, then other half cell act as a anode. When we are measuring the standard cell potential by detecting the direction of flow of current, we can decide which half cell act as a anode, which half cell act as a cathode. Suppose this standard hydrogen electrode standard hydrogen electrode act as an anode. This will be act as an anode. Then automatic, this half cell, a half cell act as a cathode. Okay, in this situation, now standard cell potential equal to, now standard hydrogen electrode act as a anode and a half cell act as a cathode. That means E reduction cathode minus, now standard hydrogen electrode act as an anode. This is the reduction potential of anode. Now for standard hydrogen electrode, this will be the 0. That means 0, 0.0. That means the standard cell potential equal to E reduction cathode, and this is the A half cell. That means the cell potential which is measured is equal to the standard reduction potential, is equal to the standard reduction potential of a half cell. That means for a half cell we measure the standard reduction potential. Suppose the second possibility, that means the standard hydrogen electrode act as a cathode. Then automatic a half cell act as a anode. This a half cell act as a anode. Now standard cell potential equal to E reduction cathode minus E reduction anode. Now standard hydrogen electrode act as a cathode. That means the standard reduction potential of cathode will be 0. That means standard cell potential, this will be 0 because cathode is the standard hydrogen electrode minus E reduction anode. That means standard cell potential equal to minus standard reduction potential of anode, and this is a half cell. So in this case, the standard cell potential we have measured whose negative value is equal to the standard reduction potential of another half cell. So in short, simple conclusion is, when standard hydrogen electrode act as an anode, then the cell potential we have measured which is equal to the standard reduction potential of other half cell. When standard hydrogen electrode act as a cathode, then the negative value of the standard cell potential is equal to the standard reduction potential of other half cell. Now reverse conclusion is also true. That means when other half cell having a positive reduction potential, other half cell, suppose say this having positive reduction potential, when this is connected with a standard hydrogen electrode, then it acts as a always cathode, and the standard hydrogen electrode act as a anode. Remember, suppose half cell having a standard reduction potential is negative, then it acts as an anode. When it is connected with the standard hydrogen electrode, and that is act as a cathode. Now by this way we can measure the standard reduction potential, otherwise standard potential of the different half cell with respect to standard hydrogen electrode. Now second point is representation of half cell and cell. how to representation. That means symbolic representation. We can say symbolic representation. Representation of a cell. Symbolic representation of cell. Suppose we have zinc half cell. That means zinc solid which is connected to its ion, that means Zn plus 2, which is in aqueous form. Suppose it is in standard condition, then 1 molar. That means both form are contact with each other, oxidized and reduced form. This is oxidized form and this is reduced form. This is known as half cell. Otherwise, it is also known as the redox couple half cell. Or it is also known as the redox couple. Remember, suppose for Cu half cell, that is Cu solid is a contact with the Cu plus 2 aqueous concentration is 1 molar. This is reduced form, this is oxidized form. Now, suppose in case of standard hydrogen electrode, inert electrode is there on which we are passing gas. Again, in certain electrode, suppose chlorine half cell is there, in which we also use the inert electrode on which we are passing the chlorine gas. So, how to write them? So, platinum provides the surface, that means platinum, this is a solid form. Again, we are passing the hydrogen gas, H2 gas, that means having a pressure 1 bar. Okay, and this is converted to H plus, aqueous concentration is 1 molar. This is the representation of a standard hydrogen electrode. Now, how to represent the complete cell? Representation of a complete cell. This is the representation of half cell, standard half cell. Now, first taking the example of a Daniell cell. So, in a Daniell cell, we know zinc half cell act as an anode, copper half cell act as a cathode. So, as per rule, in a symbolic representation of cell, anode is always written as left side. Anode is left side, remember. Anode is the left side and cathode is written as the right side. Now in a Daniell cell we know zinc half cell act as an anode, that means from here Zn solid to Zn plus 2 aqueous 1 molar. Now if we are using the salt bridge, then 2 vertical line. 2 vertical line indicate the salt bridge is used to connect the 2 half cells. And if only 1 vertical line, then it indicates that we have not used the salt bridge to connect the half cell. In this way, suppose the 2 electrodes are kept in electrolyte solution by making the partition, that means using the porous membrane, and electrolyte having different concentration, 2 electrodes is kept. In this situation, there is no need to salt bridge. Here we are using salt bridge, that 2 vertical line. This is the anode. Now cathode. Right side is a cathode. In a cathode, always a reduction reaction take place. In anode, oxidation reaction take place. That means Zn to Zn plus 2. Now in a cathode, reduction reaction take place. Remember, reduction reaction take place. That means Cu plus 2 is converted to C. That means we have to write the Cu plus 2. This is aqueous 1 molar and the Cu solid form. Remember here, Cu plus T is converted to Cu. That means act as a cathode, here act as a anode. Zn is converted to Zn plus 2, Cu plus T is converted to Cu. Now suppose we are taking hydrogen electrode. Then suppose hydrogen electrode act as a anode. Hydrogen electrode act as a anode, and the other electrode act as a cathode. Then representation. Anode is always left side. That means platinum solid H2 gas having the pressure 1 bar. Now H plus 1 molar. That means hydrogen electrode is the left side. That means it acts as a anode. Now two vertical line indicates the solvent. Suppose copper electrode acts as a cathode. Copper electrode acts as a cathode, then Cu plus 2 is converted to Cu. So Cu plus 2 aqueous 1 molar Cu. The hydrogen electrode, standard hydrogen electrode acts as an anode, copper acts as a cathode. Now suppose aluminium, we are using aluminium act as an anode. Then Al plus 3, that means metal and their oxidized form. Aluminium is in solid form, Al plus 3 aqueous 1 molar. Now solve the bridge. Now suppose standard hydrogen electrode act as a cathode. Standard hydrogen electrode act as a cathode, that means H plus. H plus is converted to H2. That means this will be totally reverse. That means H plus aqueous 1 molar is converted to H2 pressure 1 bar and then platinum solid. So it is written like this. Here aluminium is anode, standard hydrogen electrode act as a cathode. So if a symbolic representation is given, then we can decide from this which half shall act as an anode, which half shall act as a cathode. Remember, anode is left side, cathode is right side. In anode always oxidation reaction take place. In a cathode reduction reaction take place. And anode is always a negative pole, and the cathode is always a positive pole in the case of electrochemical cell.